Hi, my name is Dia, and we will be covering Homework 4, the rocket science, in context of SpaceX's Starship rocket that uses liquid methane and oxygen as propellants. For number 1, we are covering the spectrums for both CH4 and O2, as well as the before combustion spectrum, as well as the after combustion spectrum. Before all that, we have the spectrums for each of the molecules in the entire stoichiometry equation, for CH4 methane, for O2 oxygen, for CO2 carbon dioxide, and then also for H2O water vapor. Looking at the before combustion spectrum, the reactant mixture contains CH4 and O2, but since the O2 or the oxygen is inactive, since it has no dipole change when stretched, it contributes nothing. The spectrum shows methane only with 2 bands at the 3016 mark and the 1306 wavelength numbers. And more importantly, there is no peak at 2349 and no OH envelope around 3500, confirming that no products have yet been formed. And then as we look at the after combustion spectrum, the methane bands have completely disappeared in their place, and in their place, CO2 appears with a very sharp, intense peak at 2,349 wave numbers, and water vapor shows like a broad OH stretch with around 3,600 to 3,800 wave number, plus a band at 1,595. The stoichiometry is clearly and directly visible here. The equation produces 1 mole of CO2, but 2 moles of water. And by the Beer-Lambert law, the concentration determines the absorbance, and so the water bands are drawn at roughly twice the intensity of CO2, and the spectrum encodes the molar ratios.
This is Andres. Today we're learning about X-ray photoelectron spectroscopy. Some background info is during an engine test, the residue formed on a test stand, and the XPS analysis revealed 2 products, copper originating from overheated cooling components and carbon from incomplete combustion. Okay, so the copper region, which is represented in orange, around 930 to 960 eV, is measured at the copper 2p core, and the peaks at Cu2p32 and Cu2p1/2, so around here. Means that there's spin orbit splitting, and the shake-up satellite down here equals the presence of copper 2, and it proves the overheated theory, as metallic copper would not show such a strong satellite. Then the oxygen region here at around 284 to 290 eV, or the oxygen measured at the oxygen 1s core, shows that there's a composite of metal oxide, so O to Cu bonds, and advantageous oxygen, so organic oxygen from air exposure, and that the slight asymmetry on the higher binding peak towards the left means that these are the different oxygen-containing functional groups. So advantageous, metal oxide, etc. And the carbon region down up here is measured at the carbon 1s core, and the sharpest peak here is a double carbon bond, so that represents the graphitic sp2 carbon, and the peaks at the C to C to CH bond, and then the C to O bond, and then the C double bonded to O, and then the O to C, which is double bonded to oxygen, also have higher binding energies, which is also typical of advantageous carbon. And the measurements that were taken in the air mean that carbon and oxygen species will deposit naturally on the surface. Thank you.
Hello, my name is Charlize, and I'll be going over the section that covers question 3, mass spectrometry for rocket fuels. I'll be comparing 2 fuels, liquid methane using SpaceX's Starship, and RP1 kerosene using the Falcon 9. Looking at the methane spectrum first, methane, or CH4, is a single pure compound with a molecular weight of 16. Because it is a simple molecule, the mass spectrum is very clean and straightforward. The molecular ion at M/Z16 is the base peak, followed by fragments formed from sequential hydrogen loss. There are 5 main peaks in the sequence: CH4 at 16, CH3 at 15, CH2 at 14, CH at 13, and C at 12. The RP1 kerosene spectrum looks completely different though. RP1 is a complex mixture of hydrocarbons, mainly N-alkanes ranging from about C10 to C16, along with cycloalkanes like cyclodecane and small amounts of aromatics such as benzene and toluene derivatives. Because it is a mixture, the spectrum is much broader and more complex. The dominant feature is the alkyl fragment series. The butyl cation at M/Z57 is typically the base peak, with other common fragments such as propyl at M/Z43, pentyl at 71, and hexyl at 85. These peaks are separated by 14 mass units, which corresponds to the mass of a CH2 group. Small aromatic fragments can appear at M/Z77 and 91, which are characteristic of benzene and substituted aromatic compounds. The molecular ion region above M/Z140 is weak or barely visible, because larger hydrocarbons tend to fragment extensively before reaching the detector.
Hello, my name is Haley, and I did the instrumentation part. And so first I did the IR, and this is the schematic diagram showing how the IR works on a piece of paper and also the different parts to it. And this is the photo of the real instrument, and then I'll get into the explanation of each part of the instrument. So the light source emits light, and the sample holds the analyte and a monochromator/interferometer, and is used to split light and create interference patterns, and the detector measures the intensity of the light from the sample, and the signal processor receives data from the detector and uses Fourier transform mathematics to raw interference patterns. Then I talked about the XPS, and this is the schematic diagram again, showing the different parts, and this is the photo of the real instrument. And then the X-ray source, or irradiates the sample to eject photoelectrons from the core level of the surface atoms. Electron lens collects emitted photoelectrons and focuses them into the analyzer, and the electron energy analyzer acts like a band pass filter, only allowing electrons with a specific kinetic energy to pass through to the detector. The electron detector counts the number of electrons arriving at the analyzer, and the data analysis system converts raw electrons counts into spectra, enabling quantification, identification of elemental composition, and determination of chemical states. The MS, here's the schematic diagram for this one. Here's the photo of the real instrument. And the explanation is that the liquid chromatograph, or the LC, the pump delivers the mobile phase at a consistent, precise flow rate. Autosampler/injector introduces the sample into the mobile phase stream. The column separates the mixture into individual components based on their chemical properties. The interface and ion source connects the LC and MS by removing solvent and converting liquid phase analytes into gas phase ions. The mass spectrometer, or the MS part of the LC, the ion guide focuses the generated ions into a beam for efficient transfer into the mass analyzer. The mass analyzer separates ions based on their mass to charge ratio, and the detector detects the separated ions converting into or their abundance into a signal to create a mass spectrum. And finally, the data system processes signals from the detector to produce chromatograms and spectra for analysis. Thank you.